Here we will show how to run CST using characteristic mode analysis. First, let's open a new project. Create new project. We're going to do a millimeter wave and RF and optical simulation and antennas. You can choose just about any one of these, but we'll choose mobile phone and integrated. And neither of these matter, as we'll be changing it later, so time domain is fine. These are the standard units. It's going to be working in millimeters and gigahertz. And let's run our simulation from 0.8 gigahertz to 1.2 gigahertz. You can define a set of E fields or H fields, far fields in between these frequencies by clicking any of these buttons, but we'll show how to manually set those up in a minute. This will be our template name. You can change that to anything you want. Let's do CST Demo, characteristic mode analysis. And let's save our project. Let's call it CST Demo. So here in our bottom is our parameter list. Let's add a new parameter. We'll call it length. And let's have the length of our new object being 136 millimeters. Let's also create a parameter called width. And let's have it being 66 millimeters. Now we have a length and width. Let's create our new component. So we'll click the Modeling tab in the top left-hand corner. And let's create a new brick. And I tend to just hit Escape and manually enter the parameters. We'll name this Object 1, and let's have a length, start from minus length, divided by 2, to length, divided by 2. And same thing here, but minus width, divided by 2, and width, divided by 2. Let's have no height to this object. You can have different component labels. We'll keep this as component 1, and let's make this a perfect electric conductor. Click OK, and we have our new object. This is a perfect electric conducting object with these length and width parameters. We can see our component and edit it under Components, Component 1 Object, double-clicking there, and double-clicking our definition gives us our original, so we can change this at any time. Now we want to define different monitors that we would like to look at. So let's look at different field monitors, and let's add a new field monitor. Here let's do a far field RCS, and let's do a single frequency at 1 gigahertz. However, you can do a stepped width, different samples, or samples logmatic. We can also include sub-volume, and we'll look at that in a minute. So let's hit apply, and we can see we have a new far field monitor. Let's also look at an E field monitor. We'll do the same frequency, but this time let's use a sub-volume. So here we can do a free, and we can set this as minus length divided by 2, minus width divided by 2, and let's do a height above this of 5 millimeters. And we'll have this as a length divided by 2 and a width divided by 2. We want to look at the Z-plane, so if we look in the bottom left-hand corner, we can see our Z-plane is above it. So that's the plane we're going to be looking in the XY plane. So let's hit apply, and now we have a new E field. We can also do H field or other energy densities. We can see our field monitor there above it, and we can see that we're looking in that XY plane. You zoom in and zoom out using either the scroll wheel and to move it around, or these different objects here. So we can pan it, and that's a left click and pan, a 3D rotation, a left click and rotate, a dynamic zoom, left click and dynamic zoom, and a rotate in plane. Finally, let's set up our simulation. To do that, we need to go to the Home tab and change our solver to an integral equation solver. Then let's run our integral equation solver, and we need to change our source type to characteristic mode analysis. As we don't have any ports defined, this is the only type available. We will also define this as custom. Generally, we find that a higher accuracy tends to work a lot better with this software. So for this demonstration, we're going to do a third high accuracy. This takes a little bit longer, but it solves a lot of problems. We can look at any number of characteristic modes. Let's look at 6 characteristic modes. And the sorting frequency is how CST sorts these modes. It sorts it differently than other programs, as it tracks a single mode across frequency and will track that to very high eigenvalues, rather than setting a defined threshold and tracking modes in that threshold. It's a very innovative tracking method and different from other solvers. Let's apply this. And now we can start our simulation. So we're going to be running the characteristic mode analysis on the structure. CST will automatically mesh this structure and solve for the fields defined as well as the characteristic modes. So let's start this. Now the simulation has run, we can look at our 1D results. So under our 1D results, we've got characteristic mode analysis. Then it shows us characteristic angle, eigenvalue, and modal significance. Let's start with looking at the eigenvalue. Gives us each of the modes we requested, and we can see that the single mode is tracked across the frequency band of interest. We can look at all the modes by clicking this, as well as looking at things such as characteristic angle, where the resonance of a mode is at 180 degrees. We can add markers to this by pressing the M key and double-clicking where you like the marker, and then you can drag this marker. So for this particular mode, it's resonant around 0.98 gigahertz. Finally, we can also look at the modal significance. Order of 1 is a resonant mode. Anything less than 1 is a non-resonant, is not in resonance. In any of these tabs, we can look at a single mode. We've also got our 2 and 3D results. This is where our E fields show up. We can look at our E fields for any given mode in the 3D view. So let's look at it for mode 1, and we can look at our ABS, and then we can change the view properties of this. So we can look at the amplitude, and we've got the characteristic amplitude. We can also look at the phase, and the average, and the entire thing. We can run this and look at how the phase and amplitude changes across the system. Finally, we can look at the far fields, and we would expect the far fields of mode 1 to look like a dipole, as it does here. We can change our far field properties by right-clicking and going to the Properties menu. In here, we can look at E field pattern, H field, power pattern. We can also look at linear scaling and change axes. This is the basics of using CST for characteristic mode analysis.